last time we had the Fourier Bessel series defined on 0 to 1, right? So if a function fx is defined for 0 to 1, you can express the function as sum of various Bessel functions. Well, it's the same Bessel function of order n. So n is a fixed value. And this is, j and k is some constant, and the bigger this constant is, it's going to shrink the Bessel functions, right? So it's going to shrink the Bessel functions in a way that you have more fluctuations inside the interval 0 to 1. That's what's happening here. And the actual meaning of the j and k was that it was the kth zero of the nth order Bessel function. That's how I explained it, right? Yeah, but when we try to use the Fourier Bessel series for solving wave equation on a disk, we actually have to be able to solve this for 0 to L, because it eventually becomes the radial direction function. So L will be the radius of the disk that we are working with. So what I want to do is I want to convert this into the corresponding formula on 0 to L, and all you have to do is you have to stretch this Bessel function that was originally for 0 to 1. You stretch this much, right? So how do you stretch a function? You divide by the number, right? So it's like if you have sine of x, and it's this from 2 pi, then sine of 1/2 x, it stretches double, right? So it becomes like that, which ends at 4 pi, right? So to stretch things out, you want to divide by L. So that's what I'm going to do. I'm going to divide this function that we had by L of x. And if you think about it, that's exactly the same thing as the sine series. So how does the sine series look like? Sine of n pi over Lx. That's how you add the sine series. But what is n pi? That's the nth positive root of the sine function, right? Nth positive 0 of the sine function, right? And you're just dividing by L. So I'm doing exactly the same thing. J and k is the kth positive 0 of the Bessel function of order n. So that's what I'm trying to do. And in order to get AK, we have to come up with a formula like this one. And if you recall, we obtained this formula by using the orthogonality conditions. That if you had Jn kx multiplied by Jn mx with the weight function, and if you integrate from 0 to 1, if you do this, and if k and m are different, they're equal to 0. And that was necessary for us to obtain something like this, because the idea was to multiply something like this both sides, and you integrate, and for a fixed k, most of this is 0, but when this index k is equal to this index k, then it gives you non-zero value, and that non-zero value was this one, right? So, so fortunately for us, well, not fortunately, but a simple change of variables by setting u as x over L can show that even when you have L here with 0 to L, if you have this integral with u equals x over L, then this will still give you 0. And so that's something that can be done. And I don't want to do this one because it's very similar to the next result, which is we have to do the case when m is equal to k, which is you integrate from 0 to L of x times j n k x times itself, so it's squared dx. So I want to compute this one. Oh, there should be an L here, I forgot. I want to compute this using the fact that this is the integral from 0 to 1 of x jn k x dx. This squared dx. Okay, so using the fact that this value is this, I want to compute this one by doing change of variables. And it's very basic, something that only requires calculus 2 knowledge. So I just want to show you how this is done, and I'll leave this one to you because it's very, very straightforward. Okay? All right, so let's do that. So what we do is we set u, change of variables, as x over L, so that x would equal to Lu, and dx is equal to L times du. L is a constant. And if you do that change of variable, then when x is L, when x is equal to L, u becomes 1. When x is 0, u is still 0, because 0 over L is 0. X is replaced by Lu, so you have Lu here, Jn k, and then when you replace x by Lu, L and L cancel, so you just have u, this thing squared, and dx is L times du, right? But then this looks exactly like this integral, except that there you have some 2 extra L's, right? If you bring that outside, it's like L squared times 0 to an integral of integral from 0 to 1 of u times jn k u squared du. And this is the quantity I talked about. Oh, if you replace u by x, it doesn't change if you change u to x. If you change u to x, we did a whole lot of calculation yesterday, right? And this came out to be 1/2 jn plus 1 jn k, this one, right? So you end up with 1/2 L squared jn plus 1 jn k squared. So that's what we have, and owing from that, now we have a formula for AKs. So this calculation that we did, and the other one that we didn't, but if we accept that it's as simple as this one, then any function defined from 0 to L can be written as this Fourier Bessel series for any n, okay? As you can write this as you can write f as this, with ak obtained as the integral from 0 to L of the function x times the function f of x times jn k divided by L x dx. But now, to normalize this integral so that you can recover ak, you don't divide by the previous one, but you need this extra L squared, right? So you need 1/2 L squared jn plus 1 j and k squared, okay? So that will be our formula for the Fourier Bessel function from 0 to L.